The equivalent resistance, you can see, is always less than the smallest resistor. Why is it always less than the smallest resistor? So let me say we have 1, 2, 3, and 4. Remember how you calculate it. You calculate it instead as 1 over R, remember, right, plus 1 over R2, just like that. So if we do it that way, it means that we're going to be doing something like 1 over 1 plus 1 over 2 plus 1 over 3, just like that, plus 1 over 4. If we do that and then we add all of this together, you will find out that it is always smaller than the smallest resistor. Always, it's always. So let us use an example so that you will get. I did not want to make this video a calculation video, just theories, but it looks like I need to do one quickly so that you can understand where I am coming from. Okay, so now let me say they are connected in parallel, 2 and 3 connected in parallel. What is smallest? 2, Abi? So we want to find the total resistance, so the resistance equivalent. That will be what? 1 over 2 plus 1 over 3, right? By the time we find the LCM, which is 6, so we'll be having 3 plus 2 over 6, right? That gives us what? 5 over 6. As simple as that. So if you look at this now, what you are getting now, the total equivalent 5 over 6, and now 5 over 6, remember you have 1 over R, right? 5 over 6, which means that R will be what? 6 over 5. Now 6 over 5 is 6 over 5 not less than 2, which is the smallest. So it is all these steps I'm going through, and just the exam, if you come across a question like this, don't even bother yourself to start solving it. I'm just trying to prove to you why the answer is correct. Okay. All right, 42. The Kirchhoff's first law is based on the conversion of charge. Kirchhoff's second law is based primarily on the conservation of energy. Please take note of this concept. The algebraic sum of currents at a junction in a circuit is always 0. The electromotive force of a source represents the energy supplied per unit charge by the source. The SI unit of electromotive force is volts. Okay. The internal resistance of a practical battery causes a voltage to drop inside the battery when the current flows. Alright. The terminal voltage of a discharging battery are generally less than its EMF, electromotive force. Electrical power in a DC circuit can be expressed as P is equals to VI or IV. P is equals to VI or IV. Just take note of that. Alright. 50. The SI unit of electrical power is watt. Electrical power is watt. Electrical energy consumed by an appliance is related to its power and operating time. You should know how they calculate it, right? How do you get the electrical energy consumed? What you just need is the power and the operating time, and you get it. A fuse is primarily used to protect a circuit from excess current. Of course, that is why they put fuse in electrical appliances, to protect it from excess current. So when excess current is supplied to an electrical appliances, and just all of a sudden, just a boom, what happens is that the fuse automatically shuts down that electrical appliance to protect it from further damage. Alright, a conductor obeying Ohm's law is described as ohmic conductors. Which of the following is most likely to be an ohmic conductor under suitable conditions? Of course, you have the metallic resistor. 55. The current in a circuit is measured using a ammeter. Alright, a voltmeter is connected in a circuit in parallel. That's when you use voltmeter, parallel, to measure what? Potential difference, right? Potential difference. To measure volts. Alright, 57. An ideal ammeter has a very low resistance, while for volts it has a very high resistance, voltmeter. 59. A short circuit generally produces a very large current. The function of a switch in a simple electrical appliance is to open or close the conducting pathway. Yeah, of course, I know you must have seen a room or a house or something with switch, and you must have seen some without switch. If there's no switch, of course, you can't put it on, you can't shut it down, it's just always on or it's always off. Okay, so the switch is what regulates the pathway, the conducting pathway, if electricity is produced or not. A magnetic field is a region in which magnetic forces can be experienced. The SI unit of magnetic field strength or magnetic flux density is Tesla. So anything electric, don't bring Tesla to electrical. Tesla is related to magnetic. So magnetic field lines outside the bar magnet generally run from North Pole to South Pole. North Pole to South Pole. So you have something like this. I know you guys can attest to this. The arrow runs like this from north to south. Okay, magnetic field lines are imaginary lines that are used to represent magnetic field. So if you want to study, of course, imagine we are just looking at the space of air, or we're looking at air, we're not seeing anything, and you said we're studying something related to magnets. No, what they use is the field, the lines rather, the field lines. That's what they use. What is the field lines? Say, oh, this is how the magnetic field is relating to the environment, or this is how this particular charge, or this is how this particular magnetic energy is derived. You get? So it is the field line they use. The force acting on a moving charged particle in a magnetic field is your magnetic force. A charged particle moving parallel to a uniform magnetic field experiences a magnetic force of 0 magnitude. A charged particle moving perpendicular to a uniform magnetic field experiences a maximum magnetic force for a given speed. The magnetic force on a moving charged particle is always perpendicular to both the velocity and magnetic field direction. The path of a charged particle moving perpendicular to a uniform magnetic field is circular. Of course, it's always circular. A current carrying conductor placed in a magnetic field may experience a magnetic force. This one is very, very straightforward. Very, very straightforward. It's a magnetic field, so you should not be experiencing electrical force, a magnetic force. The force on a current carrying conductor in a magnetic field depends on the current, the magnetic field, and the length of that conductor. The direction of force on a current carrying conductor in a magnetic field can be determined using the Fleming's left-hand rule. A current carrying coil placed in a magnetic field can experience a torque. A magnetic dipole is commonly represented by a pair of opposite. You can see dipole, electric dipole, magnetic dipole, opposite. But in electrical, the opposite are the same, separated by a distance. All right. The magnetic dipole moment of a current loop depends on the current and the area of the loop. The SI unit of magnetic dipole is option A, 77. A magnetic dipole placed in a uniform magnetic field experiences a torque that tends to align its magnetic moment with the magnetic field. The energy stored in a magnetic field is associated primarily with an inductor carrying current. The SI unit of inductance is Henry. Self-inductance is a property of a circuit by which it opposes charges in its own current. That is inductance. The induced EMF in an inductor is associated with a change in current through the inductor. Faraday's law of electromagnetic induction states that induced EMF is related to the rate of change of magnetic flux linkage. Lenz's law determines the direction of induced current. So Lenz's law determines direction of induced current. According to Lenz's law, an induced current flows in a direction that opposes the change produces it. Electromagnetic induction occurs when there is a change in magnetic flux linked with a circuit. A transformer operates primarily on the principle of mutual electromagnetic induction. A step-up transformer is designed to increase voltage. Step up. When you get transformer, the first thing that comes to your mind is voltage. I beg you in the name of God. When you get transformer, the first thing that comes to your mind is what? Voltage. So when you say step up what increases the voltage. Step down decreases the voltage. So step down does what decreases the voltage. Down, go down, down. Okay. A transformer requires alternating currents for normal operation, of course. In an ideal transformer, the power input is approximately equal to the power output. You should know the formula NS, NP, and of course you should know that formula. Maxwell's equation provides a mathematical description of electric and magnetic field. Of course, this electric and magnetic field, they can coexist, they can happen together. But of course, somebody just decided to make that a reality. What's his name? Maxwell. So Maxwell decided to do that, and he brought out some crazy equations. Those equations proves that of course we can describe electric and magnetic fields at the same time. One of the major achievements of Maxwell's theory was the prediction of electromagnetic waves. Electromagnetic waves consist of course electric and magnetic field. Electromagnetic, electric and magnetic. Okay, so electromagnetic waves can propagate through vacuum. Okay, vacuum. The speed of electromagnetic waves in vacuum is approximately 3 times 10 raised to the power 8 meter per second. That is the velocity or the speed. In an electromagnetic wave, the electric field and magnetic field are perpendicular to each other. Please take note. They are perpendicular together. They are not parallel. They are not opposite. They are perpendicular to each other. The direction of propagation of an electromagnetic wave is perpendicular to the electric and magnetic field. You can see the same question, but it was changed. Now, see, which of the following is an electromagnetic wave? Radio wave. The electromagnetic spectrum is arranged according to properties such as frequency and wavelength. In vacuum, the relationship between the speed, frequency, and wavelength of an electromagnetic wave is represented as the speed, that C, is equals to the frequency times the wavelength.